Continuing our presentation of the polygonal model and its use in organic chemistry, we will now see how this model directly represents the presence of asymmetric or chiral carbons, a very important concept in organic chemistry. Let us consider the glyceraldehyde molecule as an example, specifically the D form, as explained ahead. Fischer's projection shows that this molecule has a ketone group and two alcohol groups in its structure. Recall that the polygonal model hydroxyls are represented by triangles, carbonyls by a square, and a carbon skeleton by a vertical line, whereas hydrogens bound to carbon are not represented. In the middle carbon of the glyceraldehyde molecule, or carbon 2, the hydroxyl is attached to the right in the structure. Would it make a difference if this hydroxyl were on the other side? Yes, it would. We can see that this carbon has 4 different bonds. Spatially, carbon is like a tetrahedron, with its 4 vertices corresponding to 4 distinct bonds. What happens if we exchange 2 of the links with each other? We find that the tetrahedrons cannot be superimposed, that is, we have 2 distinct compounds. We say that this carbon with 4 different bonds is an asymmetric or chiral carbon. In this case, these distinct compounds are called D-Glyceraldehyde and L-Glyceraldehyde. They are called stereoisomers, a special kind of isomerism. Later video will deal with the different types of isomers. In the polygonal model, we place the bond on the right in D-glyceraldehyde and on the left in L-glyceraldehyde. Unlike carbon 2, carbon 3 is not asymmetrical because it does not have all 4 bonds with different groups. So it makes no sense to place the hydroxyl on the right or left in the polygonal model. By convention, the hydroxyl linkage is drawn as a slanted line segment. A major advantage of this model is that it allows very rapid identification of asymmetry or chirality. For example, how many asymmetric carbons does the glucose molecule have? By using the polygonal model, we see that the molecule has 4 asymmetric carbons, corresponding to the horizontal bonds. Using Fischer's representation, it takes longer to perceive this relationship, as can be seen in these molecules. In contrast, in the polygonal model, perception of this relationship is very fast, so this model emphasizes this important property of organic molecules.
If you like this video, please like, share and subscribe my channel. Thank you.